Okay, so we've now looked at the nucleophilic substitution reactions, the haloalkanes. Different nucleophiles. We've had hydroxide ion, water, ammonia, and cyanide. Now change the focus a little bit. Let's think about which kind of haloalkane is going to react the fastest. Is it going to be the chloro, the bromo, or the iodo haloalkane? So these are all the same. Bromo, the only thing that's they've got the ethyl alkyl group, and the only difference is we've attached a different halogen atom to them. Okay, so I'll just remind ourselves what we've got. We've got a partial positive charge on the carbon atom there, and we're going to react then with a nucleophile. Let's say that we're going to react that with OH minus. Okay, now most people, if you ask them which one do you think is going to react the fastest, most people give a pretty sensible answer, logical answer, but it's actually wrong. Most people would say, right, I think this would be the fastest. Why? Because, well, chlorine is the most electronegative element, isn't it? Out of bromine and iodine. So that means the partial positive charge is the biggest on this one. So that's going to be the most attractive to nucleophiles. That is perfectly logical, but it's the wrong answer. What happens is, right, so it's the iodo, which is the fastest at reacting. I've got to think why. So I'm going to put an arrow here. Increasing rate of reaction. With all nucleophiles, but for example, with OH minus. Okay. Now the reason for that is down to the carbon halogen bond strength. Okay, so if we look at the bond strengths, I'm going to write them down. So I haven't actually got fluorine there, but I'll put it down. And the bond strength in kilojoules per mole. Carbon fluorine is very high. That's 485. Okay. Chlorine one is 328. Oops. Chlorine is 328. Carbon bromine 276. And the carbon iodine 240. So the bonds get weaker as you go down the group. So the CX bond gets weaker. And the reason why it gets weaker is because the halogen atom gets bigger, so the bond gets longer. The longer a covalent bond, the weaker it always is. Okay, so the reason why the iodo reacts the most quickly is because, well, what's got to happen in all of these reactions, if you just draw what's happening here, I'll draw the halogen atom as X. Here's our nucleophile coming along, OH minus. Well, that's going to attack there. And this bond has got to break. The CX bond needs to break. And this is called, you may not have got this far, but this is the rate determining step. This reaction, that's the slowest bit of the reaction, that bond breaking. So the overall speed of the reaction is determined by how readily that bond breaks. And the iodine bond is a lot weaker than the bromine, which is chlorine, fluorine, and so on. So the rate of reaction is there. Now you may notice whenever we're talking about haloalkanes, if you look in textbooks or in class or whatever, we never really talk about fluoroalkanes. And the reason why is because they don't really behave like the other haloalkanes because they're unreactive. And the reason why they don't really react with nucleophiles is because this bond is incredibly strong. So the activation energy is too high. So you may have come to things like Teflon, for example. Teflon is a polymer of, right, it's basically like polyethylene, but you've got big long chains of carbons with fluorine, CF2 instead of CH2, yeah? right? It's a polymer, and so you can coat the inside of frying pans with it stuff. It's not going to catch fire because it's just not very reactive because the carbon fluorine bonds are too strong. Okay. Anyway, so that's why we don't really talk about fluoroalkanes when we're talking about haloalkanes. Right, so we've got a bit of a trend in reactivity there. The iodo is more reactive than the bromo, which is more reactive than the chloro.